Okay, so for a resonant circuit, what you're doing is you're trying to find the frequency of that supply that will give you the supply voltage and the supply current being in phase. So you're looking for the phasor addition of IC and IRL to be in phase with your VS. So you take VS to be a reference phasor because VS, the voltage, is the same across this branch here with the capacitor in it as across this branch here with the RL in it. So that's your first thing to do, is to take that VS as being your reference. Now from what we did for power factor correction, you should remember that when you put in your IRL phasor, it's going to be somewhere in this quadrant. So for argument's sake, we'll put it there. And that's your IRL. And you're trying to find the value of IC, which would be this part here, that when you add it onto IRL, you get a phase angle of 0. So measuring that's 4. So it's the distance from the end of that phasor up to that horizontal line. So when you add IRL and IC, you get a value there of IS. And at that point, at that frequency, the circuit would be at resonance because your IS is in phase with your VS. What you should notice about this one that's different from the last one, in a series resonant circuit you can get voltage magnification. So you can get big voltages across the capacitor and the inductor compared to the voltage across the resistor. In a parallel resonant circuit, you can get big currents across the capacitor branch and the RL branch and only have a small supply current. So you get current magnification. So you get current magnification across the branches. And what you should also notice, this time, at resonance, IS is at a minimum. In your series resonance, IS was at a maximum. But in parallel resonance, IS is at a minimum. So if IS is at a minimum, your Z, which remember yesterday we talked about dynamic resistance, so dynamic impedance or dynamic resistance. If current is at a minimum, then your dynamic impedance is at a maximum. So if you're asked to draw the graphs today, you'd expect the same kind of graphs, but the labels would be the other way around. So the impedance would be the big one, the one that went up to a maximum, and your supply current would be the one that came down to a minimum. Also, because they're different circuits, the equations are different. So in your notes yesterday, parallel resonance starts on page 16. The condition for resonance, which we just talked about, is on page 19. Then you've got the proof for the formula for resonant frequency. So there's the proof for it there. You don't have to remember the proof. No one's ever had to remember the proof, I don't think. But you do have to be able to apply the formula. So in the same way as yesterday, don't throw it all in your calculator in one big chunk. Try to do it in parts. So that's your formula for resonant frequency. The other thing, page 20, was the formula. The other things we'd be interested in working out would be what your dynamic impedance or dynamic resistance is calculated as being. That's your L over CR. If you remember yesterday, for series resonance, your impedance was just your resistance. It's a wee bit different now. It includes everything. So then to get your I, which will be at a minimum, is for I equals V over your dynamic impedance. We've talked about the current magnification. You can get current magnification across the branches. Similarly, you can have a Q factor, a quality factor, the same as we had yesterday. That's your Q factor. And your equation for bandwidth is the same as the equation was yesterday, FR over Q. And it's measured the same way, but you take it from the impedance curve rather than from the current curve. And I went off the page. And that's pretty much it. Parallel resonance.